Hello everyone, this is Dilip. In the last video, I have shown my code which I wrote for neural networks. And while writing the code, I faced many issues. This video is a summary of the problems I faced and how I overcame them. This might be useful for you as well if you plan to code neural networks. So after writing the code for neural networks, the first thing I faced was how to choose the learning rate. As you know, with gradient descent algorithm, we move the weights by the whatever the derivative we get multiplied by the learning rate. So I have to choose a learning rate which is not too aggressive as well as which is not too slow. So initially I searched online and I found the most normal learning rate used to be 10 to the power of -4. But that did not work for me. That made my learning rate so slow that I am not able to make any progress in the neural networks. So it was not achieving the goal. So then I experimented with multiple values. So I started with 10 to the power of -4, then I tried 0.1, and then I tried say 10. I even went to 100,000. Then I settled at 1 because that was giving me a good result. My neural network was progressing well as whatever the result it is giving, it is also improving if I choose a learning rate of 1. So for me, this alpha learning rate of 1 worked. So I was in the last video, whatever the program I've shown, I even give the link to it. So I am initializing this learning rate just before the backpropagation. So here I'm putting the learning rate. Okay, so you can alter it and run it and see how it works if you want to experiment. So this is about the learning rate. Then next problem I faced is related to the initialization of weights. So how to initialize the weights? So what happened initially, I was just randomly taken a Gaussian distribution between -1 to +1 and then tried running the algorithm. So it was not giving me any good results. Then I modified it to take the random distribution between -3 to +3. Even then it is not giving me good result. So we know that we have to go with Gaussian distribution, but none of these methods were working for me. Then I went with He initialization that worked for me. So here I'm initializing the weights. So all the parameters. Yeah, here I'm initializing the weights. So this is the He initialization. So what are the parameters between layer 1 and layer 2? How to initialize this? You have to do it this way. So you have to take random distribution. So random, when you do, it will give random normal distribution between -1 to +1, and you multiply it with square root of 2 by first layer. So since the first layer is the input layer, so I put 2 by is. Similarly, for between second layer and third layer, since my second layer I am putting as hidden size hs, so again random distribution. How many weights I want? It is obviously hs cross 10, hs multiplied by 10. So then multiplied by 2 by hs. So this gives the initialization, which is otherwise referred to as He initialization, He initialization. So this gave me the most beautiful weights that using the backpropagation with less number of iterations itself, I was able to get a very good level of accuracy. So choosing the initial parameter is also important in neural networks. So let's move on to the next problem. Regulation parameter lambda. So I thought, like, what is the need for regularization? Since we already have neural networks where we have new set of features being calculated in the hidden layer, what is the need for regularization? So initially I went without regularization. So I just put lambda equal to 0. Then I am not getting the desired result I want. Then after putting the lambda to some value, I observed that it immediately moved my accuracy levels. It's like accuracy levels have improved using the regulation parameter. So having the regulation parameter is also important for us. So in the code where I did that, here it is. So even this regulation parameter, I experimented with 1, 10, 20 like that. So one gave me the good result. So I stuck with 1. And there is no 100 fast rule that your learning rate or your regulation parameter have to be this much. So depending on the data and how your algorithm is performing, you can alter this like you want. So whichever gives you good accuracy, you can go with those values. Let's move on to the next one. So bias neuron. So this one I ignored till end. So I thought, what is the need for bias neuron when we already have like so many neurons? Like I have around 50 neurons in the hidden layer. So what is the need for a bias neuron? What it will give? But I was wrong. So keeping a bias neuron also improved my accuracy level. So I included a bias neuron in input layer. I initialized it to 0.5 because most of my values are between 0 and 1. I initialized it to 0.5. And in the hidden layer is also there is a bias neuron. So having the bias neuron immediately improved my accuracy levels as well. So what happens if you don't use the bias neuron is the algorithm will get skewed. Like to a particular set of classes, it will get skewed. Say we are recognizing between 0 and 9. It will get skewed such that it will only recognize like 0, 1, 2, or every whatever the input you get, it will recognize as 0 to 2 like that. So it will get skewed. Having the bias neuron will prevent that skewedness. So in the program where here I have put the bias neuron. So bias neuron I'm initializing it to 0.5. And input layer size also, so 784 plus 1, so it is 785. And hidden layer also 50 plus 1, 51. So hidden layer bias neuron we do not initialize because it depends on the input weights. It automatically gets initialized to some value in the activation layer, which is the like hidden layer. Let's move on to the batch size. So I have 60,000 images for my training. And if I include all the 60,000 images for every iteration of gradient descent, like whenever I have to update the weights, if I do that 60,000 times, like it will take so much time. So it will take almost like 2 hours or 3 hours time on the Google Colab where I was doing. So again, if I have to test something, then I cannot wait for that much time. So what I did, I choose a batch size of 200. So for every 200 samples, I was immediately updating my weights, and this actually worked for me. So even the batch size, we need not take all the samples because it will slow our training, whatever we are doing. So even batch size we can customize based on us. And for me, I was choosing the batch size such that for every iteration, it's a different batch size. So first 200 samples I was doing, then I'm updating the weights, then I'm getting to the next 200 samples. So my algorithm is not getting biased towards only that particular 200 samples every time. So it's like 200 new samples every time, so that I can see my accuracy levels are improving on a new data set every time I run. So let's just take a look how I implemented the batch size. So this is how I implemented the batch size. So I put a batch size of 200 and 0 to 240 iterations. So 240 times 200, it's like 48,000. So since you have 60,000 training images, it will run without any issue. And what I am doing for k in range of L to L plus batches. So initially this L is 0. Since it batches at 200, it's 0 to 200. Then I'm incrementing L by batch size. So then L will be like 200. So again, from 200 to 400, we are iterating. So this way I'm doing. And there is a term for this as well, which is called stochastic gradient descent. So we are randomly choosing some 200 samples, and we are applying the gradient descent on it. Since why I'm saying these are random, because the 0 to 9 are not sequenced in the MNIST data set. So that way we are like randomly choosing 200 samples every time. So this is otherwise referred as stochastic gradient descent. Okay. So next thing is activation functions. What activation functions to use? So remember in the backpropagation algorithm where I was explaining, I told about the sigmoid activation function and nothing else. And my previous video, I talked about, not previous video, I think previous to previous video, I talked about activation functions of ReLU and softmax. So I was trying to use ReLU and softmax functions, and I was not getting the desired result. Then I went to my original backpropagation algorithm and just stuck with sigmoid. Then it gave me the good result. So activation functions usage is a bit tricky. So make sure, like, based on the algorithm, whatever you are following, whatever the activation function you are choosing, make sure that error value will get updated properly and you will get a good result. Then only go with that activation function. So I just use sigmoid activation function everywhere. So you can see I defined here 3 activation functions. Activation. Yeah, so this is a ReLU activation function. This is softmax activation function. But I just stuck with sigmoid and it worked well for me. So initially I was using these two, but due to some reason they're not getting good result. But again, I went back to the algorithm, initial algorithm, which I proposed, and I just, based on that algorithm, I just used sigmoid and it worked without any problem. So number of neurons in the hidden layer. This is one more important concept. So as I told, the more neurons, the better. Okay, and one layer is reasonable default. So I just took one hidden layer, but initially I was trying with since there are 784 input parameters, I was trying with 392 parameters in the hidden layer. Sorry, 392 neurons in the hidden layer. So because of this, my whole network, right, for even a single iteration to go through, it was taking more than 20 minutes for each iteration to run. So I was like, even if I have to do some modification or if I see some issue in the code, so it will, I have to wait for a long time. Then I just thought, why to go with this much complex problem? Then I researched online as well. So they have mentioned, so your hidden layer can be as simple as possible. So first try with the simplest one. So I thought, okay, so I have 10 output neurons. So I'll just put 10 neurons in the hidden layer. So this way my program was running fast and I was able to debug many issues using that. Then once I made sure like all the pieces are fitting fine and I'm getting some good levels of accuracy, then I changed the hidden layer size from 10 neurons to 50 neurons. Then my accuracy also improved. So that's why better go with simplest neural network as possible. So just have one layer in the hidden layer and have hidden layer neurons equal to the output neurons. So that is enough for us. Then let's move on to next thing. This is the transfer derivative. So the error value in the backpropagation, whatever you get, you have to multiply with the transfer derivative. So here you can see I'm multiplying with the transfer derivative, the error value. So whatever the activation function you choose, the corresponding activation function's transfer derivative, you have to multiply. So for sigmoid function, this is the transfer derivative. The sigmoid result, whatever we get in that particular neuron, multiplied by 1 minus neuron. As you know, sigmoid makes sure that whatever input you give, it always stays between 0 and 1. So that's what this also outputs. And next one is optimizer selection. So this is the tricky part. I thought like let's make it as simple as possible and go with gradient descent. Gradient descent is nothing but whatever the weight you get, whatever derivative you get, you subtract the initial weight with the subtracted by learning rate times the derivative. So this is the simplest gradient descent. So I was just doing that. Then I thought, okay, let me go with Adams initialization, Adams optimizer. So Adams optimizer helps in converging fast is what they said. So I tried with Adams optimizer as well, but it's not giving me the desired result. Then like after setting out after making sure like all these parameters are fine, like all these problems I tuned and I solved them. Then for me, better than Adams optimizer, gradient descent optimizer worked better. So I went with gradient descent itself, simple gradient descent, which is weight subtracted by learning rate times the derivative. That worked for me. So in program also you will see it is just I am calculating the gradient and then I am just subtracting weight minus alpha times gradient. So this simple thing worked for me. Okay. So now these are about the tuning, and how I tune these parameters is depending on what, like I am not getting the good result. So for verification, what I used. So initially I went with cost function. So whether cost is reducing or not. So that way I can be sure that my algorithm is working fine. Then I went with gradient checking. So gradient checking also explained in my previous videos. You can take a look at them. So this is nothing but you use the cost function to calculate the gradient, and you compare that gradient with the gradient we calculated using the backpropagation and see if they are matching. So if they are matching means our backpropagation algorithm is fine. So for me, with the cost function and gradient checking, there is some issues I faced, which is for a small batch size, these are working fine, but when I use large batch size, these are not giving me correct result. So then I went with cross validation. Cross validation is nothing but for every iteration, after updating the weights, I'm just checking whether for given 100 samples from the test data, whether my whatever the weights are calculated, whether they are giving the correct result. So when they give the correct result, then whatever the counter value is there, counter I am updating. So out of 100, how many it gives the correct values, that one I am checking. So continuously this cross validation accuracy has to improve. So this is what I have done. So for me, this cross validation also improving with time. So after whenever I am updating the weights here, immediately I am putting the cross validation, and I am checking whether cross validation accuracy is greater than 95%, then I am breaking. So here we can see this cross validation accuracy. It is 88, 90, 93, 94, 88, 88, 90. So here I can check the accuracy. So for every iteration, how much is the accuracy improving, I can check. So this is the iteration number, and this is the accuracy, like how many out of 100 they are passing. So I can take 90% accuracy this one. So like that. Okay. So ultimately, I was able to achieve that greater than 90%, like 96% accuracy. Then here it has stopped. So running the neural network is also fun with the cross-validation data set, because you can see like how your neural network is performing. And I am also printing some parameters values as well to see how they are changing. So this 0.20, how this mode modified to 0.21. So this is fun to watch whether your algorithm is improving, as well as when it is improving, you will get that good feeling that it is moving fine. So this cross validation is the easiest I found out, even though it takes some time for the calculation. Better than cost function and gradient checking, this has helped me in tuning my parameters well. So that's it for today's video. Thanks everyone for watching. Please like, share, and subscribe. Thank you.